So now that we have a good idea of what's going on with area under a curve, let's talk about how it actually applies. So we're going to talk about the relationship between velocity and displacement. So suppose for a moment that I draw you a nice generic curve like I did before, except this time we're going to express velocity as a function of time. So this curve models the velocity of an object over the course of time. You'll notice that the velocity is not constant through this interval. Rather, it's increasing and decreasing and increasing. So with that in mind, how could we use this velocity curve to estimate how much distance has been traveled? Well, for a reminder, the idea of displacement is that displacement is going to be equal to velocity times time. Now, the assumption that gets made here is that the velocity is constant. So the assumption is velocity is constant. And as you can see, the velocity is definitely not constant in this case. However, I would like to point out that if we do what we have been doing up until this point, which is take this interval and break it up into a bunch of little tiny subintervals, and then estimate the area of each of these using a rectangle. By using a rectangle, essentially what you're saying is we're going to go to the top of this and estimate the velocity, or estimate the area using a rectangle. And as soon as we make this rectangle, we have assumed that the velocity is constant on each of these intervals. Which means that for each of these individual intervals, I can take the estimation for the velocity and multiply by the time. So in context of what we're doing here, this velocity times time is going to be approximately equal to the areas of these rectangles. So one application of area under a curve is that if the curve happens to be a velocity curve, then the sum of all of these areas could be an estimation of the total displacement, or, depending on the situation, the distance traveled. So with that in mind, let's take a look at an example together where we are given a number of velocities over intervals. So the speed of a runner increased steadily during the first 3 seconds of a race. Her speed at half-second intervals is given in this table. Find lower and upper estimates for how far she traveled in the first 3 seconds. Now what I see here is that we have a total of 6 intervals over which we'll be making estimates. So the 6 intervals go from 0 to 1/2, 1/2 to 1, 1 to 1.5, 1.5 to 2, 2 to 2.5, and 2.5 to 3. So what we'll do for this is set up a left-hand approximation, and we'll set up a right-hand approximation. Now in each of these cases, I notice that the change in time is nice and consistent. The change in time is going up at half-second intervals, as was promised in the description of the problem. So delta t, in this case, would be represented by 0.5 seconds. As soon as I take 0.5 seconds and I multiply by a corresponding velocity, I will have a total number of feet traveled. So for the left-hand approximation, I am going to take delta t, and I'm going to multiply it by the velocity at. For the first interval, we use the left endpoint, so 0. For the second interval, we use the left endpoint, that's 0.5. Then the velocity at 1, 1.5, 2, and 2.5. Now real quick, this notation means the velocity evaluated at each of these time intervals. That is not multiplication. The only multiplication that takes place is the multiplication of the delta t that takes place out here. So the velocities, according to this table, would be 0, 0.5, so that'd be 6.2, The velocity at 1 is 10.8. The velocity at 1.5 is 14.9. The velocity at 2 is 18.1. And for the last time interval, again, left endpoint, that'll be 19.4. Now at this point, I'm going to turn to the calculator and ask the calculator to perform that calculation. So 0.5 in front, set up parentheses, 6.2 plus 10.8 plus 14.9 plus 18.1 plus 19.4, close the parentheses. This would be an estimate of 34.7, and the units on this, we took seconds and multiplied by feet per second, giving us an overall calculation of feet. Now for the right-hand approximation, we'll be doing the same thing, except that for each of these intervals that we have, we'll be selecting the right endpoint. Now really the only thing that changes is that the 0 that we used for the first interval will simply become the 3 in the last interval. So for the first interval, we'll have the velocity at 0.5, then the velocity at 1, the velocity at 1.5, the velocity at 2, the velocity at 2.5, and the velocity at 3. So again, right endpoint for all of these intervals. So the velocity at 0.5 we already had in here, that was 6.2. At 1 was 10.8. At 1.5 is 14.9. At 2 is 18.1. At 2.5 is 19.4. And finally, the velocity at 3 we haven't used yet, but that'll be 20.2. Now once again, if you want to use the calculator to help you out, I practically insist. So 0.5 times, set up parentheses, 6.2 plus 10.8 plus 14.9 plus 18.1 plus 19.4 plus 20.2, close the parentheses, and we get 44.8. Now, based on the description that was given to us earlier in the problem, it says find the lower and upper estimates for how far she traveled in the first 3 seconds. I would say that our left-hand approximation would be our underestimate because it is the smaller value. And here we would have an overestimate, as this one is the larger value. So the actual distance traveled, we'll use d for distance, is likely going to be somewhere between 44.8 feet and 34.7 feet. If we wanted as good an approximation as possible based off of the data that we have, I would say the best possible approximation would be the average of these two estimates. And once again, according to the calculator, actually I'm pretty sure I can get this one without the calculator, average of 34 and 44 is 39, and average of 0.7 and 0.8 is 0.75. So I would say that is the best possible approximation for how far the runner actually traveled. It was about 40 feet.